All right, here is the Laurent series decomposition theorem as I've named it, and it has the same exact setup as the Cauchy integral formula on an annulus. So we'll assume the same setup. So assume f is analytic on this annulus. And the Laurent series decomposition theorem is going to tell us that there exists G analytic on the disk of radius big R and H analytic on this complement of a disk, union infinity. So this is a neighborhood of infinity, and I'm going to say it's analytic at infinity. And F is going to equal G plus H. This decomposition will be unique if we further require that H of infinity is 0. And we get Laurent series out of this because G will have a power series centered at 0, and H, if you plug in 1 over Z, will have a power series at 0, and then if you put 1 over Z or reflect back, you'll get a power series for H involving negative powers of Z, and so then when you add them together, you're going to get a Laurent series for F. And this will have absolute convergence in A. And we can compute the coefficients from integrals just as we've done for analytic functions on disks. So the nth coefficient will be the complex line integral on the disk of radius s, where s is between little r and big R. And you just do f of w against w to the negative n plus 1 dw over 2 pi I. And this will work for n, not just a natural number, but any integer. Okay, so the proof uses the Cauchy integral formula in a strong way, so let's try to keep it handy. Oh, and before we get into the proof, maybe it's worth pointing out these analogs of Cauchy estimates that we can write down just as we did for the Cauchy integral formula on a disk. So these coefficients we've written down up here, we can bound them in this line integral by the supremum of f on the circle of radius s, and we'll also get an s to the minus n, where s is between little r and big R, and again, n is any integer, and you could again take maybe some infimum here if you wanted over s's between little r and big R. And we'll use these Cauchy estimates on the next slide to prove Riemann's removable singularity theorem. Okay, but let's prove the Laurent series decomposition theorem. So we need to break up f as an analytic function on a disk centered at 0, and then a function analytic at infinity. So here's how it goes. So we fix R1 and R2 just as we had in the Cauchy integral formula on an annulus. And for z and modulus less than R2, I'm just going to define G to be this integral that appears in the Cauchy integral formula. For z bigger than R1, I can define H to be this other integral that appears in the Cauchy integral formula here. And already I have f equals G plus H, but I want to show that G and H are analytic in the right regions. So I'm going to break up the 1 over w minus z in two different ways, and this looks exactly like the example we looked at earlier, where I was breaking up 1 over 1 minus z and 1 over 2 minus z, depending on the region I was in. So how do we break it up? Well, with g, we're going to break it up to get a power series with respect to z. So I'll pull out a w and get 1 over 1 minus z over w, and w is has modulus exactly R2, and Z has modulus less than that, so I can form a geometric series here. But in parallel, we'll do something similar but different with -1 over W minus Z. I'm going to pull out a negative Z from the bottom to get 1 over Z here and 1 over 1 minus W over Z. But now in this case, since W has modulus R1, I get a geometric series involving W over Z. So they're sort of flipped versions of each other. But these series converge absolutely and uniformly within maybe, well, the key thing here is absolute, and you have sort of bounds on all the terms. So I'm going to put these formulas into the formulas for G and pull the sum out. In the case of G, we get Z to the K, and we had W to the negative K plus 1 here integrated against F. So this is just giving us G's coefficients as a power series in terms of F. On the other hand, H, you can pull the sum out and get a formula with negative powers of Z, and here are the coefficients of those negative powers. And we want to make sure that this is analytic at infinity, so you'd put in 1 over Z to flip this to see that you had positive powers, and the same coefficients here. And the powers start at Z to the 1, so we do indeed have H of infinity is 0. And so with this, we get that G is analytic on the disk of radius big R, and H is analytic for Z's bigger than little r and also at infinity, because it's represented in this form. And that's what we need to show for the existence portion. The uniqueness part is not too bad. Let's say we have F written as in one way with G and H. So G will be analytic on the disk. Well, I think there's one thing I glossed over here is that G is only defined for Z's less than R2, and H was only defined for Z's with modulus bigger than R1. But we'll see in the uniqueness that, you know, you could do this for all different R1s and R2s satisfying this, and you could push, you know, R1 going down to R and R2 going up to big R. And so the uniqueness aspect will actually resolve this issue of that I moved in a little bit, that although G is defined on this smaller disk, we'll see that I can define one on a bigger disk and it's uniquely determined. So I know that it's defined on the whole disk of radius big R. So let's pose it that way so there's no inconsistency. Let's say G is analytic on the disk of radius R2, and H analytic on Z bigger than R1 union infinity, and we'll assume the same thing for G1 and a similar thing for H1, but we'll also assume that H of infinity and H1 of infinity is 0. So what do we get out of this? That you subtract and put the G's on one side and the H's on the other side. And now G minus G1 is analytic on this disk of radius r2, h1 minus h is analytic on z bigger than r1, but they're equal. So this function is analytic on all of c, but it has to be bounded on all of c, basically because it's analytic at infinity too. Why is that? Well, on a compact disk, it'll be bounded by continuity, but then I know that as I can examine its values for large modulus of z and bound them because it's analytic at infinity. And that will imply, by Liouville's theorem, that this function is constant, but since it's analytic at infinity and its value at infinity is 0, which you could interpret as a limit as modulus of z goes to infinity, since it goes to 0 and is constant, it has to be identically 0. So this stuff's identically 0. So G1 and G had to be the same, and that addresses uniqueness, but it also addresses this issue I mentioned above where I didn't start out using the radii that I needed to, but I could take a sequence of these R1s and that go down to little r and a sequence of R2s that go up to big R, and I could build G's and H's, and on each of these annuli that sort of exhaust the big annulus that I need, I'll get that they're uniquely determined. So G would be defined on the whole disk of radius big R, and H would be defined on the region where the modulus of Z is bigger than R. So that proves it, and the last thing we'll do is use this to prove the Riemann removable singularity theorem. Our main application of the Laurent series decomposition theorem will be Riemann's remarkable removable singularity theorem, which says that if I have an analytic and bounded function on this punctured disk, so it's a disk centered at 0 of radius r, but with 0 removed. So if it's analytic and bounded there, then f extends analytically to 0, and the key thing is bounded. And all we really need to prove this are these Cauchy estimates. So these ANs were the coefficients in F's Laurent series representation. So how does this work? Well, as we already proved, F here has a Laurent series representation valid on this sort of annulus. It's a punctured disk, but it fits the definitions from before. And by the Cauchy estimates, we can show that all of the coefficients for negative n are 0. So an is bounded by the supremum of f on a circle, but that's, since f is bounded, we can bound it by a constant, so that's what this c is here. And this holds, well, and so I have s to the minus n. This is for s bigger than 0 and less than capital R. But when n is negative, I'll get s to a positive power here, and I can send s to 0 to see that an is 0 for all negative n. So f has to be just a power series. And so it's analytic at 0 just from boundedness near the singularity. So this theorem is really important and will enable us to give a pretty detailed description of all the possible singularities of analytic functions. So if a function is bounded near a singularity, it has to be analytic. So what are the other things that can happen? Well, we'll see that in the next video series.